end of the night. Congratulations. I know it's been a long night, hopefully full of fun discussions and discoveries. Welcome to our presentation. I'm Christopher Rodriguez. I am a sophomore physics and applied math major.
And I'm Josiah Trawick, and I have the same majors, which I'm a senior.
That's crazy.
Yeah.
So we will be talking about a really cool tool that we have here on the Trevecca campus. It's called the SQUID microscope. We'll be explaining all about what that means. SQUID stands for Superconducting Quantum Interference Device. This is a super sensitive, very cutting edge, top of the line imaging device that we have here on campus. So we'll be talking a little bit about the theory behind it, but also some research and updates that we have been doing this past year. Also huge thanks to Dr. Fred Cawthorn, who could not be here right now, and the entire Neosera team. So this device is the Neosera Magma SSM, Scanning SQUID Microscope, developed by Neosera Magma Technologies. This is what this looks like. So if you ever want to spend a couple million on a pretty cool looking device, it looks like a 3D printer. That was my first impression. But what we have here is the whole staging module, where we have the SQUID is where it gets its name, is this part right here, the little funnel shaped thing. That's a sensor. And basically this whole tool is used for failure analysis. So whenever you have electronics, circuit boards, this is anything with current running through it, this machine is going to be able to scan it and find any flaws in it. We have a whole staging system underneath that will move the sample, as well as all our electronics, and down here this tower of the control boxes and our monitors and everything we need there. This is a closer look at the staging system. We have electronics coming in from all different directions. We have the smaller stack of control boxes up there. Another big important element is a cryogenic system. Since this is using superconductors, we have to get these materials super cold in order we want some quantum effects to take place here. And so that is, we need a whole cryo system with super cool gases, so we need that to be pumping in, but we'll take a look at what this does. This is a look at the SQUID sensor, which will be down here, the green part. But this is the cold head. This is where we use the cryo system to cool down this whole system. We have a few different things going on. This is what it will look like in actuality. It's about that tall. And it sits right above the sample that we're going to be scanning. This right here, this H thing, is the actual SQUID sensor. It's tiny. And right here, it's surrounded by the superconductor, and the rest, we have either silver or gold foil that's holding it in place. And we'll get to that in a second. What I thought is really cool about this device is that we have all sorts of really unique materials that go into making this work. So to start off, like I showed in the last one, some of the materials holding the superconductor in place, or the SQUID sensor in place, it's either gold or silver foil, and so it needs to be super thin in order for the SQUID to get close enough to the actual sample. Another thing is we have sapphire rods that are inside the SQUID sensor, and because sapphire has some really unique properties that we're able to use with electronics and different things, that helps with the SQUID scanning and everything that's involved with that. Copper is really important because of its conductivity with both electricity and heat, because again, temperature is super important here. So copper plays a huge role in how the SQUID is constructed. Then there's YbCO. Speaking of copper, this stands for yttrium barium copper oxide. And so in this picture, it's actually not the cool floating metal thing, it's the black thing on the bottom, and it's what a lot of superconductors are made out of. And so that's part of the SQUID sensor. And then at the very tip here, there's actually, like, the window is made of diamond, because it's going to get really close to the sample. We don't want it to get scratched or obstructed in any way. We want it to be as clear as possible to get the best image possible. All right, so that's a lot of the hardware. This is the software that goes into analyzing all the data that we get from this sensor. So the SQUID sensor is detecting magnetic fields, which are created by any kind of current. You pass a current through anything, there's going to be a magnetic field there, and this is going to detect it. What's cool about this program is it's all made in LabVIEW. A lot of electrical engineering and physics majors like us, we learned this starting out, but this is just at a whole crazy different level. We have all these little things called sub-VIs in here. There are thousands of them in this process. Just so many functions built on top of each other, and so we've been able to do some really cool things with that. Basically, what happens is that with the superconductor, since it's a quantum process, there's going to be a non-linear signal from the superconductor, and so we have a little box that was on the picture earlier. It's called a flux lock loop. That's such a tongue twister, and it's basically going to create bias points in the response that is going to help us basically average out signals so that we do get a linear response that we use later. Then, whenever we're testing something, we're going to run an AC current through it. So it's going to be alternating, kind of like a sine wave function. And but what we want to do is apply this linear response to that function. So what we're going to do from the AC current, we're going to apply a Fourier transform called a window function using a lock-in amplifier. And so that's going to let us apply the linear response from the flux lock loop to the function and be able to transfer that into a pixeled image that we're going to see in a moment.
So here's some kind of gimmicky scans from the actual SQUID. What you may not know is a lot of your ink and toner is slightly magnetic, and so when you print things, you actually have little tiny magnetic fields. And so by just running the SQUID DC current, so it's all very easy to handle, we don't need to go through the flux lock loop, we can scan kind of our regular objects. That's a dollar bill. This is a little printed Trevecca logo. And just the magnetic fields on the prints, the SQUID is so sensitive, we actually can pick up images just like this without even running currents through our samples. What happens much more often though is because we're dealing with circuits and we're trying to fail test things, we are running currents through the samples, so we are injecting some sort of voltage into the thing we're actually trying to image. And it's going to come through different wires, and so this is going to be a little wire, and for those of you who have had enough physics or math, you'll know the right-hand rule, and so our current is traveling through our wire, and that'll go the direction of your thumb, if you've seen this before, and that will create a magnetic current that curls around in the direction of the right hand, and that's why we call it the right-hand rule. And so you can see with this loop, what we're measuring is the Z component of the magnetic field. So essentially the magnetic field that's pointing up. And so in this case, if we're curling, we get to a down magnetic field. And so that will represent by the SQUID in a red display. And then when we see up on this other side, we'll represent that with blue. Now what happens right over a wire is we'll get a 0 value for our B. Our B in the Z direction. And so that'll get displayed as a white line. And so this is kind of a beginning indication that we're over some sort of wire when we're imaging.
Perfect. So this is a close-up video, actually the video if we can play it too, of what, this is the tip of the SQUID sensor as it's right above our circuit board that we're testing. So you're going to see it lower down, and it's going to get crazy close to the thing. It looks like it's touching. This is a super zoomed in image, but it needs to get close enough to be able to detect those magnetic fields from the current that's being run through. We have testing boards that we're able to control the current running through at different areas if we want. So you'll see it's going to start moving back and forth, scanning across it, kind of like a 3D printer again. It's like just very expensive 3D printer that doesn't print anything. And so the data that we get from this on the next slide, as we'll see, this is what happens when we scan a little loop of current. So this is, on our board, this is kind of what a loop would look like. This is tiny. This is what it looks like under a microscope. But basically, we're running current through here, around the loop, and back. This, after cutting through like all this noise and static here, we confine it to this image, which, as we talked about, you can see kind of the shape of the wire, of the loop of the wire here. Because that's that's in the white. You can see it extending. Then outside and inside is going to be different colors because that's how you see the magnetic field coiling around the line of circuit there.
And so it may seem nice to just be like, okay, cool, I get my image, and then I just look for the white lines and I get my wires. Like, that's super easy. Of course, electromagnetism is far more complicated than that. So what we have here is an optical image, and it's a little tough to see, so I'll describe it. So we have a wire coming right down here, and then we have two little off-branch wires. These two are important because you can kind of see on this image, there's no really way to tell that there's two wires. And we also get this weird white zone right here, and it's like, is there a wire there? But it's all these different currents interacting with each other, making magnetic fields that aren't so clean as when we have nice little circles or lines. And so what happens is we take a magnetic field input, and those of you who have had enough physics would recognize the Biot-Savart law, which from a current we can get a magnetic field. Essentially we have to inverse that process because we need to get a current density from a magnetic field, and so we do what we call Lorentz transformation and then use a convolution, and those mathematical tools help us get a function for the current density from the magnetic field. And now we can plot the current density, and you can see this ends up being a lot more accurate. So we have our wire coming up, and then maybe hard to see if you're in the back, but there are now two recognizable wires here. Also interesting to note, if you know Kirchhoff's laws, this kind of follows where we have a larger current coming here, it reaches some sort of junction and splits off. The darker red represents less current, and so you'd have a current that kind of splits off, and these currents would add to that current. And so that's kind of how we deal with, this is not even complicated yet, but that's how we deal with some of the complications of circuit designs.
All right, so that's kind of how the SQUID works normally. What we've been working on over the past year is a few different things. First of all, at Trevecca, a few electrical engineering students have been able to serve as interns for the company Neosera Magma. One of the things we've been working on is building an opens control box, which is going to allow us to use the SQUID to scan open circuits, which would be really helpful because a lot of times circuits won't work because there's a break somewhere in them, and so we'll be able to scan for those. We've also been kind of rewiring some of the systems, connecting things, updating all of it according to the schematics that Neosera would give us. And one of the things we were running into was a problem with just different temperature readings that weren't really making sense. So we did a gas exchange on the cryogenic system. We had to flush out entirely the old gas that was in the system and put in a new mixture of propane, ethane, neon, methane, and nitrogen. And so that new gas was able to give us some new data that we liked better. And then this is going to be a picture of the opens control box that we created here at Trevecca. And it's you can see it's pretty complicated, and it's pretty cool to see, like, from here. This was all done by students at Trevecca that is now going to be used in this system.
And so an issue that we kind of ran into while trying to get this system back up and running this semester is we had this strange temperature oscillation in our actual SQUID temperature reading. It's maybe easiest to see on this graph, but we had this red line shows the temperature of the SQUID. This white line shows the temperature of what we call the cold head, and that's the top of the cryo vacuum chamber. And this is nice and flat, which is what we want, and that's because we can control this. This is what we were reading, and if you have any ideas of what's going on, let us know in the questions.
Because we don't know either.
We never were able to figure it out. These periods are about a 3-hour time window, and it was oscillating about 1 degree. And so we did a whole bunch of stuff, gas exchange, a whole bunch of things, and we could not figure out what this is. So we use software to kind of cheat our way back to something usable. But if you have any ideas, let us know. So what we did is essentially we can control this cold head temperature, and so we just use it as a compensator. So if our red got too high, we just lowered our cold head, and that would lower the temperature of the SQUID. If this got too low, we would just raise the temperature of the cold head. This got us back to almost a flat line, enough to have scans again, but just a weird issue that we've experienced this semester.
So wrapping up, these are some things we'd like to continue with the project. Finishing the opens box that we created and getting it functional so that we were able to have that capability. We want to add a new motor encoder for the the stage moving so that we can have more precise calibrations, that we can hit exactly where we want. And also just a better lighting system from newer models that Neosera has. We want to come in and update the version that we have here on campus. So lastly, as you can see, like this covered a super wide range of different fields, from like electromagnetics to electronics design, software development, as you saw from the lab view, and different uses of the C program, mechanical design with the SQUID and all the materials and everything, and then data analysis and modeling from everything we've been doing. So that's really what got us interested. It's such a wide-ranging project, and it's really getting us inspired, and hopefully some of you are all inspired to look more into this. But yeah, I know this covered a lot of stuff, so we're ready for any questions y'all have. Thank you so much for coming.
Yeah. Yes.
You mentioned some quantum effects. What are these quantum effects?
Yes, so you have, there's a wide variety, but when you have the superconductors, essentially you have two close superconductors, so you get a bunch of different quantum tunneling and different things like that. But mainly it's the super cooled superconductor that allows for the zero resistivity across the little SQUID, which is like 4 millimeters wide. That's able to give it that super sensitivity to magnetic fields, because it just can go without resistance essentially.
Let's call it Josephson junction. After probably someone very smart.
Josephson.
So I'm curious about do you know anything more about why the sapphire is helpful?
It's due to its like super ability to not. It's like a super insulator, essentially, is why we're using it, and so that the SQUID actual could be very controlled without being influenced by temperature from outside.
Okay.
But yeah,
And it's super interesting.
and it's cool.
Yeah, we threw that in there. We threw a lot of information at you. It's cool stuff.
So does that all mean, like, does that mean it's also super fragile? Like, if it's so aware of, like, you say magnetic fields or whatever, like, can it be damaged easily by things getting too close to it, or?
Well, that's so in some ways, yes. That's for certain things, like we have a diamond window on there, so like nothing can hit it.
Right.
At certain times where we were running the scans, we had to take our phones out and put them at a different part of the room, because then because different things being emitted from the phones would throw that off. Something that did show up in even some of the graphs that you saw. All the equipment that's in this building will kind of give off a frequency of about, like, just combine all together, will give off a frequency of like 60 hertz, and that's kind of, like, you can't escape that.
Right.
So even in the tiny downstairs room that we have, so that was something that we had to compensate for in the programming, like knowing we can't escape this. So it's sensitive enough to pick it up. Like, you can tell the difference from when you open and close the door. That was a big thing, whether the door was open or not. But that's all the things we have to compensate for, because it's really very sensitive. Yeah. That's why it's so special. So cool.
Do you know of other applications besides circuit board analysis for the SQUID?
You could do some general imaging, anything that like carries. So, yeah, I would imagine you could like scan different metals and superconductors and get some interesting things off of that. Just off the top of my head, I would imagine you could tell like the percentage of the superconducting that a material is.
Right.
Just based on how the current flows through that.
What's really valuable about this technique is it's non-invasive. So like a lot of companies and producers, they want to be able to test their stuff, but if a component is hidden way inside something else, it's really hard to be able to get into it and like be able to take it apart and test it. Different applications of this technology is able to just take the whole thing and be able to scan through it and find issues without having to take it all apart. So that's really valuable for bigger companies that we've got.
That's awesome. Any other questions? Oh, take it.
Is there any analysis you can do with maybe magnetic domains?
What do you mean by that?
Certain materials have, how should I explain this? Maybe, certain, say you have a material, and then in this material you have, say, particles that have a associated, I believe, angular momentum that produce a particular behavior that this material has. Just help me out.
Yeah, those little magnetic domains that were in a permanent magnet, you could resolve
sure.
those.
Right.
Yeah, that's an interesting question.
We have a sample of that, of something kind of like that in the greenhouse somewhere. Might be nice
Let's
to
take it
Yeah.
down. Let's go. Let's go.
Because I would imagine that would be pretty interesting because you wouldn't have to run a current through it, but you could still measure a bunch of different things about the magnetic field. I don't know off the top of my head, but I'm sure it would definitely be scanning something because it's emitting magnetic field. Which, that'd be interesting.
We'll go add that to our next steps slide.
Yeah.
We'll go do that next.
That's interesting. Yeah.
Jeff, we're out of time. Thank you.
Appreciate it.
Good job.